To make the study easier, let's consider a 2D structure of the silicon crystals. Assume that phosphorus atoms with 5 valence electrons are injected into it. Here, one electron is free to move. In this structure, when the electrons get sufficient energy, they will move freely. Let's try to make a highly simplified solar cell only using this type of material. When light strikes them, the electrons will gain photon energy and will be free to move. However, this movement of the electrons is random. It does not result in any current through the load. To make the electron flow unidirectional, a driving force is needed. An easy and practical way to produce the driving force is a p-n junction. Let's see how a p-n junction produces the driving force. Similar to n-type doping, if you inject boron with 3 valence electrons into pure silicon, there will be one hole for each atom. This is called p-type doping. If these two kinds of doped materials join together, some electrons from the n-side will migrate to the p region and fill the holes available there. This way, a depletion region is formed, where there are no free electrons in holes. Due to the electron migration, the n-side boundary becomes slightly positively charged, and the p side becomes negatively charged. An electric field will definitely be formed between these charges. This electric field produces the necessary driving force. Let's see it in detail. When the light strikes the p-n junction, something very interesting happens. Light strikes the n region of the PV cell and it penetrates and reaches up to the depletion region. This photon energy is sufficient to generate electron-hole pairs in the depletion region. The electric field in the depletion region drives the electrons and holes out of the depletion region. Here we observe that the concentration of electrons in the n region and holes in the p region becomes so high that a potential difference will develop between them. As soon as we connect any load between these regions, electrons will start flowing through the load. The electrons will recombine with the holes in the p region after completing their path. In this way, a solar cell continuously gives direct current. In a practical solar cell, you can see that the top N layer is very thin and heavily doped, whereas the p. Thanks for watching Ocentra Group informative videos. Please subscribe our channel for more informative videos.